I think we'll start. Okay, guys, hi. So thank you for the last session of the conference. We're gonna hear about Do2. This is a transparent PCS with small proofs and falsifiable assumptions. What could we ask for more? This is with Benedict Bams, Tushar Mupuri, Eliraz Shirzad, and Shriram Sridhar, and Tushar will give the talk. You switch off the mic by any chance? The top.
Yep. Hi, everybody. Thanks for being here. Yeah, I'm Tushar. Today I'll be talking about Do2. It's a new transparent polynomial commitment scheme, and this is joint work with Benedict, Alireza, and Sriram. Okay, so let's start with what a polynomial commitment scheme is. It's a tuple of 4 algorithms, starting with a setup algorithm, which takes as input an upper bound on the size of polynomials that can be committed to, and outputs a commitment key and a verification key. Second, there's a commit algorithm, which takes as input the commitment key and a polynomial and outputs a commitment to the polynomial. Third, there's an open algorithm that, given a commitment, an underlying polynomial, and an evaluation point, z, outputs a evaluation proof, which is then handed over to a verify algorithm, who chooses to accept or reject the proof pi that the underlying polynomial evaluates at z to y. Completeness asks that if p of z is indeed y, the verifier accepts an honestly generated proof. And knowledge soundness says every accepting proof has an underlying valid polynomial that we can extract. Okay, so what are the properties we care about? The first and perhaps most important is a transparent setup, which means that the setup algorithm only requires public coin randomness. And this is because if your setup algorithm was trusted and your private randomness is compromised, you can no longer rely on knowledge soundness, and people can prove false statements. In fact, the workaround to this problem in systems that actually deploy trusted schemes is to destroy the machines that the setup ceremony was run on. Okay, before I talk about the rest of the efficiency measures that we care about, let me motivate why we care about PC schemes. It's because prior work has shown that PC schemes, in conjunction with this thing called polynomial interactive oracle proofs, yield snarks, which are proofs of computation. And the efficiency of the snark is directly proportional to the efficiency of the PCS. It sort of inherits, there's no overhead. And so we care about the commit and open time of the PCS. We care about the verification time of the PCS. And we care about the proof size. And we want all of these to be sort of as small as possible. Okay, so let's look at what kinds of transparent PC schemes we already have. The first row here is sort of a state-of-the-art hash-based scheme. And hash-based schemes are pretty great all over the board, except they have kind of large concrete proof sizes. Bullet proofs is a slightly older group-based scheme that has very small proofs, but unfortunately does not have a succinct verifier. And DOI has sort of improves in bulletproofs to bring the verification time down, but it compromises on proof size. And then there's this interesting line of work which has really small constant proof sizes, but at the cost of having cubic prover time. And our work sort of bridges this gap by building on these techniques actually, presenting a PC scheme with log-log proof sizes and quasi-linear prover time. Okay, so let's get into it. How does the setup algorithm work? Well, our setup algorithm relies on groups of unknown order. all it does is it samples a group of unknown order, which we will denote additively, and a generator. A group of unknown order is a group where it's hard to find the order of the group or any subgroup given a generator or more. Okay, why are these things interesting? Because they can be used to commit to unbounded integers, as opposed to other groups which can only be used to commit to like field elements and so on. And the commitment is pretty simple. All you have to do is, to commit to V is to output V times G, where integer scalar multiplication denotes repeated addition V times. Okay, and what are some candidates of groups of unknown order? We have RSA groups, we have class groups, and we have Jacobians of hyperelliptic curves. These two are in green because they do not require a trusted setup. And another thing to note, I guess, is that in our work, we sort of, okay, so prior work like Dew and Behemoth proves their schemes secure in this idealized group model called the generic group model. We sort of distill out the property we need from this idealized group model into a falsifiable assumption and prove our work secure in this, and of course show that this holds in the generic group model. Okay, so let's look at how we can commit to a polynomial. Since we already know how to commit to integers, the natural thing to do is to encode the polynomial as an integer. So given a polynomial p, let's define p tilde of x to be the corresponding integer polynomial where you've raised each coefficient to its corresponding representative in the integers between 0 and q minus 1. The commit algorithm, given a polynomial, first computes its integer representatives. And for some fixed alpha that's larger than q, it computes p tilde of alpha and outputs a commitment to p tilde of alpha. Yeah, let's look at what this looks like, I guess, for q equals 7 and alpha equals 10. Let's say your p tilde was 3x squared plus 2x plus 4. P tilde of alpha turns out to be 324. And two interesting things to note here is it's not super evident here, but these encodings are additive. That is, if you were to encode, let's say, 1, 1, 1, and you added it to this, there is some homomorphism here. And also, given an integer encoding, you can recover the polynomial by decomposing base alpha. So how do we open and verify? Well, we use another interesting property of these integer encodings, which talks about their products. Given an evaluation point z, for now we're going to assume z is randomly sampled. And if it was not so, we could sort of randomize it using some checks. So this isn't a big deal. Let's define the vector r to be descending powers of z. Let's look at what happens if we multiply the integer encodings of p and r. You get this expression that sort of we can group into coefficients of powers of alpha. And the one we care about in particular is the coefficient of alpha raised to n minus 1. All the terms to the left we're going to call s. All the terms to the right we're going to call u times alpha to the power n. And this thing here we're going to call t. And notice that t is sort of exactly the inner product of p tilde and r tilde flipped left to right. And that, because of how we've defined r, is p tilde evaluated at z tilde. And we can recover the field evaluation, like the evaluation of the polynomial over the field, by just computing the remainder mod q. Okay, so this leads to the following strawman construction for open and verify, which is, and recall that the commitment is p tilde of alpha times g. The prover and verifier, or the open and verify algorithm, both compute r tilde of alpha. The open algorithm outputs the s, t, and u we've just seen. The verify algorithm checks that r tilde of alpha times cm is equal to s times g plus t times g plus alpha to the power n times u times g. We can move this around a little bit to see that we've sort of enforced the exact expression we saw in the preceding slides. One thing to point out here is a succinct verifier can't really compute this itself because this is a pretty large value, but we address this in our paper by outsourcing this computation also to the prover, where the prover just tells you what R tilde of alpha is and sort of gives you a proof of that. But that proof is easy to verify because R is very structured. Okay, so are we done? Unfortunately not, because even for an honest prover with an honest P tilde and an honest R tilde, if we pull this expression back up, the values of S, T, and U are far too large. Their bit length is at least N, and this means that they cannot be sent in the clear. So what do we do? Okay, let's sort of go back for a sec. Yeah, notice that all the verifier ever does with these things is look at S times G, T times G, and U times G. So could we just have the prover directly send S times G, T times G, and U times G? Unfortunately not, because for soundness, the verifier has to be convinced that the underlying integers satisfy the appropriate bounds. So we need to construct range proofs. That is, we need to have a way to give someone a commitment to T and convince them that T lies in the range A to B. And notice that T is in the range A to B if and only if T minus A times B minus T is non-negative. So I'm going to tell you how to convince someone of a proof of positive exponent, and we can reduce range proofs to this using some algebraic manipulation again. Okay, so just to reiterate, a proof of positive exponent is a proof where someone holds a commitment to T, and they will be convinced that T is non-negative. Okay, how do we do this? Well, the most important or the most useful building block we have is this very surprising result that shows that in groups of unknown order, there exists an efficient proof of squared exponent. That is, you can convince someone that some h contains an integer that is a squared, x squared, with proofs that are only size order of lambda bits. And this is independent of the size of x. So the proof size and the verifier time are both independent of the size of the integer being sort of talked about, which is very interesting. And now that we can talk about squares, well, I guess why did I bring up squares? Because we have this thing called the Lagrange four-square theorem, which says that a integer is non-negative if and only if it is the sum of four squares. And so here's an idea for a proof of positive exponent. Have the prover compute the Lagrange four-square decomposition of T and send over hi defined to be xi squared times g and the POSE proofs for each i. And the verifier checks that the POSE proofs pi I for each hi are valid, and that for all I, and the h is the sum of the hi's, which then convinces it that this equation holds. Okay, great. So now we have to be done. Except no, this takes cubic time to compute. And we tried sort of improving this for a bit. It won't budge. And this is actually where the cubic prover time in prior work comes from. So what do we do about this? We propose the following. We decompose non-negative integers into more squares. In particular, we show that every non-negative integer can be decomposed into log n many squares. And this can be done in quasi-linear time. So are we done? Still no, because if we were to do an analogous thing to the earlier slide, we would be sending over log n many group elements and proofs. So instead, what we have the prover do is commit to all the xi's in a single commitment using a Pedersen commitment. You would have to modify your setup to output multiple generators to do this, but that's still okay because there's only log many generators. And then we use this new thing that we built called a self-inner product argument to convince a verifier that for h equals t times g and this commitment c, the underlying integers satisfy the following equation. The inner product of this vector with itself is t. which is precisely this. So let's look at the proof size here. This self-inner product argument is essentially, if any of you are familiar with bullet proofs, it is sort of the same idea lifted into the groups of unknown order setting. And so the size of the proof is logarithmic in the size of the statement. And since the statement is log n size, the size of the proof is log n. And so this gives us due to a transparent PC scheme with quasi-linear prover time, logarithmic verifier time, and quite small proof sizes. Along the way, we've removed the dependence on the generic group model and instead replaced it with a falsifiable assumption. And another thing that I didn't mention here is we extend this POSE thing to handle more complicated claims over the underlying integer, where the proof size remains order of lambda. And the verifier time might depend now on n, but the interesting thing is we can handle sort of any sort of predicate that can be expressed as a efficiently computable arithmetic circuit, integer circuit actually. Okay, so there are some open questions still, which is, can we improve the prover time to be linear like most other group-based schemes while maintaining small proofs? And since the only place we really used groups of unknown order is in the POSE construction, could you construct a plausibly post-quantum secure POSE and then use sort of our blueprint to build a PCS? Yeah, that's it for me. Thank you for listening.
Okay, we have time for questions. Okay, so I have a question. So first in practice, kind of we would want not just a PCS, but we would want like many polynomials and many evaluation points. Kind of is this batching friendly?
We don't show it in the paper, but yes. And you would probably use the fact that, you would use the fact that the integer encodings are additive. Like I said, that's actually where that would come in. And yes, they're batchable. We just haven't written it down. Okay. I think. Okay, I'm 99% sure they're batchable.
That's enough for me.
Yeah.
Another question is, so in terms of like practical runtime, you have to choose some groups. And like, is this also like practically efficient?
What does the runtime look like in practice? We haven't implemented it, but we've estimated based on how much time it takes to do group operations in class groups, let's say. And it looks like for polynomials of size 2 to the 26, 2 to the 28, your prover time might be in the tens of minutes. So it's not quite competitive, but yeah. There is hope that you could like sort of multi-thread and like optimize some other things in the implementation to do better.
Okay. Okay, let's thank the speaker again. The next talk is on extractability of the KZG family of polynomial commitment schemes. And Christian will give the talk.
Okay, where do you want to go? Oh.
Okay, thank you for the introduction. This is joint work with Belahores, Dvořák, Hoffman, Hubáček, and Pastyřík. And first, I would like to give a little bit of motivation why we would want to prove extractability of any polynomial commitment scheme in the first place. And polynomial commitment schemes are typically used in compilers from polynomial interactive oracle proofs into snarks. So in the PIOP, we have a prover and a verifier. And the prover, as part of the interaction, sends to the verifier these oracles to polynomials. And the verifier can query these oracles at some points where it wants to. To turn this into a snark, we would usually use a polynomial commitment scheme. The prover, instead of sending the oracle to the polynomial or sending the polynomial itself, would instead commit to the polynomial. And when the verifier would like to query that polynomial at some point, he would send the point to the prover, and the prover would respond with the evaluation as well as an opening proof. So you can imagine that if the prover in the polynomial commitment scheme itself is able to convince the verifier without actually having any polynomial, then the snark wouldn't be secure. And so for knowledge soundness of the snark, in the standard model, we need to prove knowledge soundness of the polynomial commitment scheme also in the standard model. Some snarks like Plonk and Halo rely on a univariate polynomial commitment scheme, for example, univariate KZG. And some other snarks, for example, some check-based snarks rely on a multivariate KZG or multivariate polynomial commitment scheme, for example, multivariate KZG. The evaluation binding of the univariate KZG was proven in the original paper by Kate et al. In 2010 in the standard model under the SDH assumption. As for the extractability, that was proven by Campanelli et al. In 2020. However, it was proven in the AGM. Lipma et al. Then showed extractability in the AGM OS model. And then finally, in 2024, they showed extractability in the standard model using a new assumption ARSDH. We would want the same extractability and evaluation binding also for the multivariate KZG. The evaluation binding, at least on average, was proven in, again, the original paper by Papamantu et al. In 2013. As for the extractability, Chan et al. In 2017 proved extractability, but only of a modified version of the scheme and under a non-falsifiable assumption. So in our work, we managed to prove the extractability of the plain scheme of the multivariate KZG using a falsifiable assumption ARSDH. And this ARSDH is a generalization of the ARSDH from Lipma et al., where we generalize the assumption for multiple variables. So just to recap, the polynomial commitment scheme is an interactive protocol between a prover and a verifier, where the prover commits to some kind of polynomial. The verifier, then when it wants to open the polynomial, the verifier sends some kind of alpha to the prover, and the prover computes the evaluation z, as well as some kind of proof pi. And the verifier will check some kind of equation relying on the commitment and the proof, and will either accept the proof or reject it. The security properties that I talked about are evaluation binding and knowledge soundness or extractability. With both of these, we assume that the prover can do whatever it wants. So the prover doesn't necessarily have to work with a polynomial. The prover can send any elements that it would like to, but we know that if the scheme is evaluation binding, then the prover cannot open the polynomial that it is working with at two distinct points. So the prover cannot, for one alpha, create two evaluations, z and z prime, and two proofs, such as both of these proofs would be accepting. And this, in some sense, tells us that the prover, whatever it is doing, is at least working with a function. An even stronger security property is knowledge soundness. There, we would want the prover to be working with a polynomial. And the question is, the usual way how you would prove knowledge soundness is we would interact with the prover, and from that interaction, we would extract a polynomial. And the polynomial would have to explain the behavior of the prover, and this is also why knowledge soundness is also called extractability. So the question is, how do we formalize this notion of knowledge soundness? We took a little bit of a different approach to how it is normally done. We've looked at the polynomial commitment scheme as a proof of knowledge of a polynomial. So the difference here is that the verifier, instead of asking at any specific point alpha, will ask at some random alpha. And so this is a proof of knowledge. And this is not how polynomial commitment schemes were introduced or how the authors thought they would be used. However, for example, for the compilers from PIOPs into snarks, this is sufficient because there the verifier will ask at a random point. And this allows us to very clearly define what is the knowledge soundness, because now we can say that the polynomial commitment scheme has knowledge soundness if this proof of knowledge of a polynomial or this POCOP is an argument of knowledge. It is also useful in a sense that we can reuse other results from proofs of knowledge without having to reprove them for the setting of polynomial commitment schemes. So when analyzing knowledge soundness, in reality, we would have a prover and a verifier. And the prover would interact with the verifier and would be able to convince the verifier with some probability epsilon. In the analysis of knowledge soundness, what we instead have is an extractor. And this extractor interacts with the prover multiple times. And from that interaction, the extractor wants to extract a polynomial that would explain the behavior of the prover. And the most natural strategy how to do this is to, of course, interpolate. So the extractor will ask at some kind of interpolation domain, then interpolate a polynomial f from the transcripts. And the polynomial f would naturally agree with the messages so far sent by the prover. However, what we still need to prove is that the polynomial would also be consistent with the commitment sent previously by the prover. So if the prover is able to convince the verifier with some probability epsilon, then we want to extract a polynomial and prove that it is consistent with the commitment with some probability epsilon minus something negligible. And to show you how we prove this, I need to introduce KZG. So univariate KZG relies on this really simple but useful proposition that f at alpha is equal to z if and only if we can find a quotient polynomial such that fx minus z can be written as q times x minus alpha. And so the prover, instead of proving this evaluation claim, f at alpha is equal to z, can instead prove this polynomial identity. So the prover will compute this q, send this to the verifier, and the verifier will check this polynomial identity at some point t. To do this, pairings are used. So we have 3 groups and a pairing from the first 2 groups into a target group. I don't want to go into much detail here, but the important thing is that the prover can evaluate the polynomial f at some point t without actually knowing the point t. So the prover can use this commitment key that has some kind of basis evaluated at t to evaluate polynomial f at t in the first group, and this will be the commitment. As for the proof, the prover would compute the quotient and also commit to this quotient in the same way. Then the verifier would check the second equation that we saw on the previous slide, but would check it in the target group using the pairing. And so the verifier would check that the commitment, which is f at t minus z, is equal to the quotient at t times t minus alpha. As for the multivariate KZG, it is really similar. It also relies on this proposition that is generalized into multiple variables. So we know that f at alpha is equal to z if and only if we can find this time n quotient polynomials, q1 through qn, such that we can write fx minus z as a sum of the quotients times xi minus alpha I. And the scheme looks really similar to how univariate KZG works. The commitment is, again, the polynomial evaluated at some point t. And this time we have n proofs. And each of these proofs is the quotient polynomial that the prover commits to. Again, the verifier would check the second equation from the previous slide using the pairing. And so when we want to prove knowledge soundness, we will do it in 2 steps. We will first prove spatial soundness, and then prove from spatial soundness knowledge soundness. And in spatial soundness, we assume that the extractor already has these kind of transcripts from which he can interpolate a polynomial. So the extractor already has transcripts with regard to alpha 0 to some alpha mu, such that the alphas are an interpolation domain and all of these transcripts are accepting. Then we can interpolate the polynomial. What we need to prove is that the polynomial will be consistent with the commitment. And because these transcripts are accepting, for each of these transcripts, we have the verification equation from the scheme that holds. And each of these verification equation, in some sense, talks about the consistency between the commitment C and the evaluation Z. And so what we would ideally want to have is, instead of all of these verification equations, we would want to have one equation that instead talks about the consistency between the commitment and the polynomial. And this is exactly what we can do with use of a batching lemma and the assumption ARSDH. These two things allow us to combine these equations into just one single equation, this time talking about the consistency between the commitment and the polynomial. And so if ARSDH is hard, then we know that the polynomial that we interpolated is consistent with the commitment. This batching lemma is a generalization of the batching lemma from Lipma et al. There they proved the batching lemma for a univariate case, and they proved it by case analysis, and so they were unable to generalize this for multiple variables. What we've managed to do is we've managed to prove this batching lemma directly, and so we were able to generalize it to multiple variables. As for the assumption ARSDH, like I said, it's again a generalization of the ARSDH from Lipma et al., generalized to multiple variables, and we've analyzed this assumption in AGM and GGM. So we've proven spatial soundness. Now from spatial soundness, we want to prove knowledge soundness. So what we have to show is that we can, in fact, get such a set of accepting transcripts where the extractor would be able to interpolate. And this is really where we can reap the benefits of the definition of POCOP, because we can reuse a result from Atema et al. Called forking lemma, where the result is basically that, yes, you can extract such a set of transcripts from which you will be able to interpolate. And we can do this as a black box. We don't need to reprove anything for the setting of the polynomial commitment scheme. So in summary, we have proven knowledge soundness of multivariate KZG. However, throughout the years, other KZG-like variants have been introduced. For example, hyperpianist, where hyperpianist allows for distributed proving on the side of the prover. And what all of these variants have in common is that these changes are on the side of the prover. And so we were able to extend this proof of knowledge soundness to all of these variants. So not only have we proven knowledge soundness of the multivariate KZG scheme, but also of all other KZG-like schemes. We've defined the proof of knowledge of a polynomial, or a POCOP, and this captures the definition of knowledge soundness really well. It allows us to use other results from proofs of knowledge, and and it is sufficient for the compilers from PIOPs into snarks. One additional contribution that might be of independent interest is that while studying the multivariate KZG, we have realized that usually the prover, to compute these proofs, these quotients, he would sequentially divide fx minus z. But we've realized that these quotients can be in fact written explicitly. And so this in particular allows us to compute these quotients in parallel. And that would be everything. Thank you for listening.
Questions? Okay, let's thank the speaker again. Wojtek? Oh. Okay. Okay, so the next talk is functional commitments and snarks for P/Poly from SIS. A long list of authors, Wojtek Wee, and I guess Wojtek will give the talk.
Okay, thank you for the introduction. Thanks for staying for what used to be one of the last 3 crypto talks. Also, thanks for being a part of the 20th anniversary of my first talk at crypto. So I'll be talking about functional commitment and snaps for circuits from the SIS assumption. Hopefully my last talk at crypto too. But so for most of this talk, I'm going to focus on functional commitments. So let me just do a quick recap of what functional commitments are. So in functional commitment, we want to be able to commit to a long input X to produce a commitment sigma. We have an open algorithm that later on, given a function f, produces an opening to f of x, and we have a verification algorithm that checks the validity of this opening. The main requirements we'll be looking at for this talk are a succinctness requirement, which says that both the commitment and the opening should be very small, sublinear in the length of x, and we require that verification is fast, so much faster than computing the function f. The security requirement here is evaluation binding, which says that it's hard to compute a commitment together with openings with 2 different values. Note that this binding requirement is a bit weaker and does not guarantee any form of consistency or extractability as seen in some of the previous talks. The main result of this work is a new functional commitment scheme for circuits or P/Poly from the SIS assumptions. The scheme achieves a constant size CRS, constant size commitments, and an opening that grows to the depth of the circuit. Moreover, the verification time is linear after a pre-processing phase that depends on the function f. In addition, we also get a transparent CRS, namely that the CRS is actually public coin. I want to say that this is a substantial improvement over prior algebraic lattice-based functional commitment schemes. In particular, we rely on the standard SIS assumption, whereas prior construction relies on non-standard variants of the SIS assumption. Moreover, the prior constructions also incurs an additional multiplicative factor in all of these parameters, that's polynomial and depth of the circuit. As an immediate corollary, we get a new snap for P/Poly from the SIS assumption that does not rely on random oracles. The parameters are similar to those of our functional commitment schemes: small CRS, small proof, and small verification time. Also, we get a transparent setup and unambiguous proofs, which means that even for yes instances, it's hard to come up with 2 different accepting proofs. This is the first snap from a mini-crypt assumption. Prior constructions rely on DDH or RWE. And moreover, our construction is extremely simple and elementary and avoids a lot of the heavy technical machinery used in prior works. So for this talk, I'm going to focus on our construction of functional commitment schemes. And then the snap basically follows as an immediate corollary. Okay. So I'm going to start with a functional commitment scheme for circuits from a prior work. And here, this construction relies on a stronger assumption, a non-standard variant of the SIS assumption called succinctness. The exact details of what succinctness means is not that important because we're only going to rely on standard SIS. Moreover, this construction requires much larger parameters. The exact kind of these parameters are not important because we're going to get something much smaller too. Okay, so let me start by describing this prior construction. So in the CRS, we are going to have a very wide matrix B of dimension m by m, which corresponds to basically our cis matrix. In addition, we have L matrices, W1 up to WL, of the same dimensions as our B matrix. Okay, these are uniformly random matrices over ZQ to the m by m. Finally, we have L square matrices with 0, 1 entries. The CRS is going to contain a couple more terms, but let's first focus on these terms. The commitment is fairly straightforward. To commit to a bit vector of length L, we just basically take a linear combination of the W matrices. So this is the natural lattice analog of the Patterson commitment scheme. Okay. To compute an opening to a circuit F, we proceed in 2 steps. First, for every index I, from 1 to L, we're going to expand our initial commitment C into a GSW encryption of the bit Xi under the public matrix P. Okay. So this is going to be, what this means that we're going to compute a low norm matrix Zi such that C times Vi, where Vi is a matrix from the CRS, is of the form B times Zi plus Xig. Okay. Next, to be able to compute this low norm Zi's, we're going to require publishing additional L squared Gaussian pre-images in the CRS. And this is why the CRS is large, and this is where we don't get transparent setup, and we don't get security from the cis assumption. It's this B inverse Gaussian pre-images that are needed to compute the Zi's. Okay. Once we have this Zi's, or this GSW ciphertext, we can perform homomorphic evaluation of this GSW ciphertext to produce C sub F, which would be an encryption of F of X, thanks to homomorphism from GSW. The final opening is going to be the encryption randomness for this eval ciphertext C sub F. Verification is fairly straightforward. It basically just checks that we have the appropriate randomness for this eval ciphertext. Okay. Binding is not too hard either. Intuitively, if you can break binding, you can cancel out C sub F on the left-hand side and produce a cis solution to the matrix B. The reason you don't get security from the SIS assumption is that you have this additional Gaussian pre-images in the CRS. So security relies on succinct cis, which basically says that cis is hard even given these additional pre-images in the CRS. To get to our main construction, which relies on the standard SIS assumptions, we're going to focus first with relaxing the requirements that we can expand C into a GSW encryption of the bit Xi. This relaxation will allow us to get rid of this Gaussian pre-images in the CRS, thereby allowing us to achieve both transparent setup and binding from the standard SIS assumption. However, this relaxation comes with certain costs. First, we don't quite get GSW ciphertext. We get something much weaker that only allows us to support a weak form of homomorphism. So we're going to show you what this weak form of homomorphism is in the second step, and how to bootstrap this weak form of homomorphism to get functional commitment for circuits. Another downside of this relaxed commitment scheme is that the Zi matrices has huge dimensions that is grows with L squared instead of constant. So in the third step, we're going to show how to reduce some of these openings from L squared to constant. Okay. So in the next rest of this talk, I'm going to focus on the first step, namely how to relax this requirement that we expand to a GSW encryption of Xi, and thereby achieve binding from the SI assumptions and remove this Gaussian pre-image from CRS. Okay. So here's our new commitment from the SIS assumption, and we want to relax the following relation. First, it's convenient to move Xig to the left-hand side, and next we make the following 2 modifications. First, we replace the left-hand side with a taller matrix of dimension 2n, where the top part is CVI and the bottom part is SIG. Okay. Next, we're going to replace the matrix B on the right-hand side with similarly a matrix of height 2n and something that's much wider. From M, we're going to increase to L squared M. What does this matrix B looks like? It's essentially going to contain all these cross terms that used to appear in the Gaussian pre-images. Right. So this blows up the dimensions of the width of B and hence the dimensions of the Zi matrices. So this is what our new relation looks like. So we're going to call this new taller, wider matrix on the right-hand side B. And correctness is fairly straightforward. You can sort of isolate the terms that depend on I and the cross terms and check that this is basically where how your opening is computed. Right? In particular, you no longer need these Gaussian pre-images. You just need to know the bit size. All right. To prove binding, here it's not hard to show that under the standard SRS assumption, the top part of the B matrix is going to be a hard-sys instance, and that basically gives you binding. So basically, if you manage to break binding, you are going to be able to cancel the CBI's part on the top left-hand side, which corresponds to binding a cis solution to B top, which again is a hard-sys instance from the SRS assumption via BMR type argument. All right, so now how do we handle multiplication? To handle multiplication, we basically want to start with openings Z1 and Z2 that satisfy the two equations on top and derive an opening that satisfies the equation on the bottom, corresponds to the opening of X1, X2. Okay? This looks very much like GFW homomorphic multiplication, except the terms are split with a CB1 on top and X1G at the bottom. So you can start exactly as in GFW homomorphic multiplication. You multiply both sides of the second equation by x1 and multiply the both sides of the top equation by G inverse of CB2. And then you end up with this cross terms, x1 CB2, which you want to cancel out. The problem is that they are not properly aligned. One appears at the bottom, the second equation appears on top. So to be able to cancel out this term, we just need to pad these matrices with extra zeros so that the cross terms are aligned in the middle. And now you can add everything up to get essentially what you want with an x1, x2G at the bottom. This still falls a little short of what we want because if you look at the top, the expression, the product on the top left-hand side, it's not of the form C times V, but that's something you can do using a trick from my Eurocrypt paper. You can rewrite basically this the complicated product on the top left-hand corner as the product of two matrices, one of which only depends on the commitment, and the other only depends on the B matrices from the CRS. And now if you sum this equation up as linear homomorphic, you actually immediately get a commitment scheme that supports fast verification for degree 2 polynomials. Now, what happens for general circuits, though? We want to have general depth D circuits. The problem basically is that with this approach, you're going to have a blow-up that is linear in the degree of the computation. So for depth D circuits, this could potentially be a computation of degree 2 to the D, and the dimensions of the matrix is going to grow exponentially with D. So it's going to have a 2 to a D blow-up. So we don't want to do this. Instead, we're going to take a different approach, which is the so-called chainable functional commitment framework from some prior work. Let me just first say what the construction looks like. Commitment stays roughly the same as before, and opening now looks a bit different and proceeds as follows. When you want to open to a circuit F, you look at the wire. Wire values for this circuit F on input X. And you commit to each layer of the circuit. So the wire values for every layer of the circuit. So you're going to have these separate commitments, one for each layer of the circuit. Then you provide commitments, openings, showing that the commitments for each pair of adjacent layers are consistent. Okay? The point is that each pair of adjacent layers correspond to a degree 2 computation. So now what you need to do is to construct a new functional commitment scheme for degree 2 computation with long outputs, where instead of opening to f of x, you want to open to a commitment of f of x. So this allows you to prove consistency of each commitment with the commitment for the next layer. And this is something you can do with the previous construction we just described by using the fact that we can already support degree 2 computation. And now to support commitment of f of x, we use the fact that the commitment scheme here is linearly homomorphic. So you can support additional linear homomorphic computation without additional complexity to the construction. All right. Now, we still have the problem that these Zi matrices have huge dimensions, so we need to compress them from size L squared to L. And the idea here is to do a Merkle-style recursion. The base case is going to be L equals to 2m squared. Why 2m squared will be clear in a couple of slides, but 2m squared is really just a constant here, Pauli in our security parameter. All right. In the recursive step, we want to be able to commit to a vector of length L, given a way to commit to vectors of length L over 2. Okay. So given an input vector of length L, we're going to split it into two parts, x0 and x1, each of length L over 2. We're going to use our inductive construction or recursive construction to individually commit to each of these vectors, x0 and x1. This produces two commitments, which are matrices of dimension n by m. Then we're going to concatenate these two matrices and compute the bit decomposition of this concatenation. This is going to be a bit vector of length 2m squared, basically 2nm times log q. Okay. And now this is a vector of length 2m squared. We can then use our base case commitment to commit to this vector, and that is our final recursive construction. All right. And then you can sort of do a bit of math and check that you can actually compute the opening that satisfies our verification relation. That's basically the entire construction. To conclude, we constructed new functional complement slugs for P/Poly from this assumption. There are two open problems that I really like. The first is to construct a version of this result for uniform P, where you get fast verification without preprocessing. Such a result will correspond to a non-interactive analog of the celebrated GKR proof system under the SIS assumption. Another is to improve the proof size from linear in the circuit depth to constant. This is something that we already know from the LW assumption using CI hashing and heavy machinery. What's not clear if we can do this from SIS, or for that matter, do it from LWE, but without all of those heavy machinery. That's it. Thank you.
Questions?
Thank you for the talk. I was wondering, in case you will want to get hiding for those commitments, will it be possible to potentially call in LWE and then get something for hiding on those initial commitments?
Sorry, my hearing is a bit challenged. Can you just repeat?
If you want to get hiding for the commitments.
For the hiding?
Yes.
That's the
Can you call in
hiding.
LWE and then get
That's an excellent question. So there's some sense in which, because the question is whether you can get hiding for the commitment. First of all, the commitment is compressing. So inherently, you lose some information. But as is, we do not know how to show that the commitment scheme is completely hiding. In particular, we don't even know how to show that the marginal distribution of the commitment is uniformly random. But it seems quite, yeah, I think that's a good open problem. In the prior construction, we have some techniques to do randomization. It's slightly less clear whether they will work in this setting.
Thank you.
Yeah, hey, very nice. Are there, I think maybe you've mentioned this before, but are there certain functions for arbitrary functions, the verifier time is going to be linear in the function, of course. Do you know if for structured functions like polynomials, it's better? Like
Good. How long does it take to compute the opening? It's going to be the case that if you can preprocess separately on the X and the F, the verification time is actually constant.
Okay.
Yeah, but it's basically the verification basically. Yes. It just basically multiplies the commitment sort of slightly in an appropriate tensor form by some other matrix that sort of preprocess and then check some linear algebra constraint.
But it certainly is linear in the depth, no?
Yes. So you're going to, you're right. The computation time is going to be linear in the depth of the circuit. Yeah.
Okay.
But for a lot of natural computation at polynomial commitments, the depth is basically polylog vectors.
Okay, let's thank Hotek again. So we have one more talk, the last talk of the conference. This is an online talk. So this is about polynomial commitments for Gaulier rings and applications to snarks over Z to the decay. And Song Lee is going to give the talk.
Good afternoon, everyone. I'm Song Lee. It's a pleasure to present our work on polynomial commitments for Gara rings and how apply it to snarks over Z2K. This is joint work with Yu Haojia, Chao Pingxing, Yi Zhouyao, and Chen Yuan. Snarks are succinct, non-interactive arguments of knowledge. In a circuit satisfiability setting, snarks allow a prover to convince a verifier that he knows a witness W such that C of XW is equal to 0 without revealing this witness. Here C is a public circuit and X is the input. The proof pi produced by the prover should be short and fast to verify. Usually, snarks satisfy the properties of completeness, soundness, and succinctness. Modern snarks follow a two-step recipe. First, construct a succinct interactive argument of knowledge by using polynomial interactive oracle proof (PIOP) and polynomial commitment scheme (PCS. Then make it non-interactive using the Fiat-Shamir transformation. However, most snark constructions work over large finite fields, while real-world programs often use arithmetics modulo 2 to 64 or 2 to 32. This motivates the construction of snarks directly over Z2K, and this is the main focus of our work. So, what makes building snarks over Z2K challenging? For polynomial interactive oracle proof, the Schwarz-Zipf lemma, which ensures polynomial interpolation doesn't hold over Z2K, a common fix is to embed the computation over Z2K into a larger extension ring, namely the Galois ring, but this comes with significant overhead. For PCS, known constructions relies on pairing discrete logarithm assumptions or proximate test of linear codes over finite fields. These theories are currently leaking over Z2K. There are some known results, each with trade-offs. The first one is Renokia. They are snarks designed for Z2K arithmetics, but suffers from larger proof computation, requires designated verifier, and relies on trusted setups. Zero-knowledge virtual machine are snarks developed for computer programs. It translates computer programs to CPU simulation circuits, but in general, this can yield huge circuits. For example, ECDSA verification requires millions of RISC-V instructions. Recently, Wei, Zhang, and Deng propose a transparent snark over Gara ring. They generalize the breakdown PCS to Gara rings by using expand code. But when applying it to Z2K, this will also introduce large embedding overhead. So we address these limitations with three main results. First, we prove a proximate gap for resolved code over Gara ring. Based on this result, we construct Frey-based polynomial commitment schemes over Gara ring that support fast Fourier transform, and a Lihero-based PCS where FFT is not required. Second, we construct efficient polynomial interactive oracle proofs for the R1CS relation over Z2K. We use the reverse multiplicative friendly embeddings to reduce the embedding overhead. Finally, we implement all our constructions based on the NTL library. So among these, the proximate gap for resolved code over Gara ring is our main contribution. So the rest of this talk will focus on analyzing this result. First, a Gara ring is an extension over Z2K. Formally, we denote by GR2KD a degree D extension over Z2K, which is constructed by taking Z2X modulo a degree D polynomial fx, where fx modulo 2 should be irreducible in Z2. The principal idea generated by 2 is a unique maximal idea, and the quotient ring GR modulo 2 is isomorphic to a finite field of size 2D. Let capital T be the pre-image of F2D under this isomorphism, then T star forms a cyclic multiplicative subgroup. Moreover, the difference of any two elements in T is invertible in this Galois ring. Therefore, the Schwarzschild lemma holds over this set T means that any non-zero polynomial fx has at most degree f roots in this set T. Similarly, we can define Reed-Solomon codes over Galois ring by evaluating polynomials at points inside the set T. Precisely, a Reed-Solomon code defined over a domain L with root rho is a set consisting of all evaluations of polynomials of degree less than rho L at the domain L. It has minimum distance rho L minus rho L plus 1. We can also use fast Fourier transform to encode Reed-Solomon code, but in the Galois ring, we choose the domain L to be a multiplicative subgroup of T star of order 3 to m. Note that X3 splits a polynomial fx into 3 smaller polynomials f0, f1, f2, each with degree at most degree f over 3. X3 also shrink the domain L to a smaller domain L3, which has size reduced by a factor of 3. So repeating this folding m times, we can evaluate f at the domain L with complexity L times log L. So in a polynomial commitment scheme, a proof first to commit to a polynomial f and then prove its evaluation at a randomly chosen point sent by the verifier. The commitment and the proof should be short to efficiently verify. A popular construction of PCS combines an interactive oracle proof of approximate for linear code with a Merkle hash. An ROPP aims to prove a given vector f is close to the linear code C. Here, delta close means that the relative Hamming distance of this vector to C is at most delta. A well-known example is Frye-based PCS. I won't go into details of Frye, but recap some properties. Frye works to check whether a polynomial, given its evaluation at a domain, is close to a Reed-Solomon code. The idea is folding by fast Fourier transform. The proof first fold the polynomial fx in this way, where the challenge alpha is sent by the verifier. Note that this folded polynomial has smaller degree, at most degree f over 3, and is evaluated at a smaller domain L3. So the proximate test of f can be reduced to the proximate test of this folded polynomial. To ensure correct folding by the prover, the verifier should do some consistency checks. So the round-by-round soundness relies on the distance preservation of Reed-Solomon code, which says that if the original polynomial f is delta phi from the Reed-Solomon code, then this folded polynomial is also delta phi with a high probability. The final soundness error is 1 minus delta to t plus epsilon. Here t is the number of consistency checks. So a larger delta allows a smaller t and in turn reduce the computation and the proof size of Frye. The distance preservation comes from proximate gap for linear codes. Precisely, we say that a linear code admits a delta epsilon proximate gap if the following holds. Assume U0 to US are S plus 1 vectors in FQ of length L if for many, say, at least epsilon L gamma in FQ such that the linear combination of this UI are delta close to the linear code C. then these vectors ui are themselves data close to C. Furthermore, there exists a common agreement set E of size at least 1 minus delta L and S plus 1 code words Vi such that each ui agree with Vi at this common set E. Formally, delta epsilon proximate gap guarantees that either all these linear combinations are data close to C, or only a small fraction are data close. As we mentioned before, in the coded PCS, a larger proximate gap delta implies a better performance of PCS. So what is the upper bound of this delta? For general linear codes, it was shown in the Lihero that this delta can reach to the 1 minus rho over 3 and can be further improved to this 1.5 Johnson bond. For Riemann codes, Bensas et al. Pushed it to 1 minus rho over 3 gap and by using the Blankenberg decoding algorithm, and even further to this Johnson bond by using list decoding. So in this work, we generalize the number 1 and the number 3 proximate gap from finite field to Gara rings. Actually, the number 1 is also proved in this PKC 2025 paper, but our unique decoding bound for Riemann codes over Gara rings is better than the first one. So next, I will introduce the challenges when we generalize this half proximate gap for Riemann codes from finite field to Gara rings. So in the field case, given this vectors V are such that for many gamma, their linear combination are data close to the code C. The idea is to find S plus 1 Riemann code Vi and a common set E such that for all alpha in E, these two polynomials in Z are equal, meaning that their coefficient Ui alpha and Vi alpha match for all I. So in other words, from the left hand, we can interpolate a polynomial in X with a coefficient in FQZ. And our goal is to find a Riemann code defined over FQZ in this form. So this Riemann code can be found by using the Blankenberg decoding algorithm over the rational function field FQZ. Precisely, we can first interpolate UIX from this vector, so UI, and define by variety polynomials WXZ in this way. From assumption for many gamma in FQ, Wx gamma is data close to the Riemann code, implying that the following Blankenberg linear equations for some capital AXZ, BXZ is solvable over the rational function field. Moreover, we can using the Cramer's rule to find a solution such that this capital AXZ and BXZ are actually bivariate polynomials. So with these two AX and BX, according to the linear equations, we have A alpha Z divides B alpha Z over FQZ for all alpha in the domain L. We actually have L such alphas. According to the unique decoding bound, for many gamma in FQ, we also have AX gamma divides BX gamma over FQX, and we have at least epsilon L such gammas. So if this degree condition holds, then the Polish-Choke-Spearman lemma says that AXZ divides BXZ as bivariate polynomials. So let Px be the quotient of Bx divided by A, then Px can be written as some V0x plus V1xz plus Vsxz to S, where each Vix has degree less than rho L, and this will act as a designed rhizome code that we need, because from this equation we can get that these two polynomials are equal for those alpha such that A alpha Z is non-zero. So to generalize the proof from a finite field to Galois rings, we are faced two challenges. First, solve the Blank-Capell-Wilczek equation over GRZ instead of FQZ. But note that GRZ is not a domain, so the Cramer's rule cannot be used. Second, the original Polystroke-Spearman lemma is stated over fields, so we need to formalize a PS lemma over Galois rings. So we use the finitely generated modular properties over a local principal ring, such as the Galois ring, to solve the first challenge. Then we use the p-adic lifting technique to formalize a new PS lemma over Galois rings. In this way, we can finally prove the unique decoding proximate gap for rhizome code over Galois rings. Based on this result, the construction of a polynomial commitment scheme are straightforward. So in the Frey-based PCS, we use the fast Fourier transform over Galois rings. And in the Ligero-based PCS, where FFT is not necessary, because we can use some faster polynomial evaluation to do the encoding of ASCII code words. So these two, in these two polynomials, the proof time, proof size, and verify time are the same in the field case. For the construction of polynomials interactive oracle proofs over Z2K, I won't introduce the details. These slides are provided only to give a high-level overview of our constructions. So finally, for the experimental results, we implement the Frey-based PCS and the Ligero-based PCS over Galois rings. We implement the reverse multiplicative friendly embeddings for the first time, and based on this, we can implement our construction of PIOP over Z2K. We target on 122-bit security, so we use a Galois ring with extension degree 162. We have to admit that our results are slower than the result over finite field, but the main reason is lack of optimization for Galois rings in the NTL library. So these are some benchmarks of our constructions. To sum up, we prove new proximate gaps for rhizome code over Galois rings. We construct two polynomial commitment scheme for Galois rings and polynomial IOPs for Z2K. Combine these two, we get snacks over Z2K, and we implement our constructions. So one open question is to generalize the Johnson radius gap for rhizome code to Galois rings by using the Goswami-Sudanis decoding, and this can improve the soundness. So thank you for your attention.
Closing remarks in the main theater.